Welcome to section 15.4. In this section, we are going to be very briefly looking at applications of double integrals. At this point in the course, our primary focus is on fundamentals and being able to get practice with the use of double integrals, but we take a small diversion here into a more applied field, and that is with the topic of center of mass or center of gravity. So the coordinates x bar, y bar of the center of mass of a lamina. Lamina is just like a flat, thin, like plate, like a thin layer that we can balance on a particular point. The center of mass of a lamina occupying the region D and having a density function rho of xy. This is a Greek letter rho. It looks like a P, but it's kind of a little more curly than a P. To find the center of mass, we're going to take 1 over little m times the double integral over d of x times rho of xy dA. And that's going to be the formula for x bar. And then for y bar, we get 1 over little m times the double integral over d of y times rho of xy dA. And this is where the mass given by little m is equal to the double integral over d of rho of x and y dA. Okay, so we have some region D, some flat, thin, like plate or like a sheet, and we want to find the center of mass. The center of mass, like if we were to take this and try to balance it on like a single point, so we just put it, on something like this. We try to balance it. The only point where it would perfectly balance would be its center of mass. Okay? Anywhere else it would tip and fall over. So we're trying to identify where that point is using simply the mass of the lamina and the region, right? The formula that defines the region D. A bit of just terminology here. So as a note, the integrals in the formulas above, so this integral and this integral, they do get their own names. These are called moments, and they're abbreviated capital M sub x and capital M sub y. We're not really going to be using this terminology, but sometimes you can see, like in the textbook or in other sources, they refer to the moments of a lamina, and the moments are just the values of these integrals. So if you see that terminology, that is what that means. So let's take a look at an example. Find the center of mass of a triangular lamina with vertices 0, 0, 1, 0, and 0, 2. If the density function is given by rho of xy equals 1 plus 3x plus y. All right. In order to find the center of mass, we need x bar and y bar. So we're going to need a few things here, including the mass. So let's go ahead and get the mass first. As you can see, I have my diagram down here. So we're going to find the mass. That's going to be the double integral over d of the density function. So 1 plus 3x plus y dA. So we need to figure out how to set up this double integral, whether we want to vertically or horizontally integrate it. In this particular case, because these are all linear, there really is no one better way to do this. I'm just going to stick with vertical integration here. So we're going to go from bottom line to top line up here. So this bottom line here, this is y equals 0. This top line we can create between 2 points using like algebra techniques. So we get that this is the line y equals negative 2x plus 2. And this over here is x equals 0. So if we integrate vertically, so we have 1 plus 3x plus y, dy dx. Y is going from 0 up to this line. So from 0 to negative 2x plus 2. And x is setting the edge, so here and here. So that's going to be x going from 0 to 1. So we can go ahead and evaluate that innermost integral with respect to y. So that's going to be y plus 3xy plus 1/2 y squared, evaluated from 0 to negative 2x plus 2 dx. So we would substitute this in to every y value. Okay, and then sub in the 0. It just so happens the 0 in this case gives us nothing, so we don't have to worry about that one. But if you plug in this value into all of the y's, expand everything out, distribute, combine like terms, all of that good stuff, we end up simplifying it down to 4 times the quantity 1 minus x squared dx. So a lot of terms do cancel, end up simplifying themselves down a little bit. So this, when we take the antiderivative with respect to x, gives us 4 times x minus 1/3 x cubed, evaluated from 0 to 1. So 1 minus 1/3 is 2/3 times 4 is 8/3. So we have the mass is 8/3. So we're going to need that for both of the formulas, for x bar and for y bar. Now the process of integration here is going to be pretty similar for both of these cases, because we just did an integral that is very much alike these two, except these two also have an extra factor of x and y in them. So we'll have to take that into account. So they're not exactly the same, but they should be fairly similar. So we're going to set up x bar first. So this is 1 over 8/3 double integral of x times the density function. So let me just go ahead and multiply everything in here by x. So that's going to be x plus 3x squared plus xy dy dx. The region D is still the same, so we can set up the bounds exactly the same way for all of these. So between the 0 and the top line, and then x going from 0 to 1. 1 over 8/3, we go ahead and just take the reciprocal of this, so that's going to just be 3 over 8 instead. Outer integral is still intact. Antiderivative in here with respect to y, we get xy plus 3x squared y plus 1/2 xy squared from 0 to negative 2x plus 2 dx. So we substitute in and simplify where we can. And it works out fairly similarly, not exactly the same, but we get 4 times x minus x cubed dx. So if we go ahead and the 4 can come out and cancel with part of the 8. So we're just left with 3 over 2. And then 1/2 x squared minus 1/4 x to the 4th from 0 to 1. Ends up just giving us a 1/4, which multiplies to 3/8. So we have x bar is 3/8, which was just the coefficient. So that means that this whole integral just worked itself out to 1. And then for y bar, this goes pretty similarly. So we get 3 over 8, double integral. Everything's getting multiplied by y this time. So we have y plus 3xy plus y squared dy dx. And again, the region is the same, so the bounds will be the same. So we get 3/8 integral 0 to 1. We have 1/2 y squared plus 3/2 xy squared plus 1/3 y cubed from 0 to negative 2x plus 2 dx. This one ends up leaving us with a little bit larger polynomial, but we can take out 2/3 from everything, and we end up left with 7 minus 9x minus 3x squared plus 5x cubed dx. And at that point, there's a little bit of cancellation that can happen here. 3 with 3, 2 with the 8, so we're just left with 1/4 out in the front. And if we take just single variable, single integral, we'll just cut to the chase here. We end up getting 11 over 16. Oops, not just 6. 11 over 16 for this. So y bar is 11 over 16. So the center of mass for this triangular region is going to be the ordered pair 3/8 comma 11/16. So that is our center of mass. And if we go back and try to identify where this is, 3/8 is a little bit less than 1/2. 11 over 16 is just a little bit less than 3/4, right? So this is a little bit less than 0.5. This is a little bit less than 0.75. If we go back to the diagram here, and we go, this is 0 to 1, so 0.5 is going to be somewhere around here, and it's just a little bit less than that. And then this is 0 to 2. So we go 1 is about here, 0.75 is about here, and a little bit less than that right there. So center of mass should be somewhere around there, which I think visually that kind of makes sense, right? This seems like it's kind of towards the middle here. And again, this is just an estimate, but somewhere towards the middle, the larger part of the region, right? Most of the density and the mass will be sitting over here, but not necessarily exactly in the middle, because this corner goes a bit longer than this one does. So there's a bit of a balance to be had there. Okay, so, but that is our center of mass. So I did say this was going to be just a short section of application, and that is the end of section 15.4. So when we come back in section 15.5, we'll be looking a little bit further at another use for the concept of double integrals before we get into some new topics in the second half of the chapter.